Hi students, welcome back. So in this part, we'll be discussing about our inner transitional elements. So at the end of the part, you'll be discussing about the difference between the transition element and F-block element. So you'll be also knowing the properties of the F-block elements. So let's start our part. Introduction to inner transition elements. Electronic configuration. So electronic configuration of F-block elements. So the general configuration of lanthanides may be given as 4F, 2 5S2, 5P6, 5D021 and 6X2. So lanthanides are outer 3 shells incomplete, right? So it is to be noted that the filling of 4F orbitals in the atoms is not regular, right? It's a very important thing. This is the first important thing. The filling is not regular. So a 5D electron appears in gadolinium with the outer electronic configuration of 4F7, 5D1, 6S2. So this is because the 4F and 5D electrons are about the same potential energy and the atoms have a tendency to retain stable half-filled configuration. So this is a very important point. So whenever we have a 5D electron, right, that 5D electron, for example, if it is present in gadolinium whose atomic number is 64 and it has the electronic configuration of 4F7, 5D1, 6S2, what happens is that the 4F and 5D electrons are the same potential energy. So because of that, filling of 4F orbitals is in the atom is not regular. So on the other hand, filling of F orbitals is regular in tripositive ions. So after losing outer electrons, the F orbitals shrink in size and become more stable. So that's why PM is the only synthetic radioactive lanthanide. So this is a very important point. So filling of F orbitals is regular in tripositive ions. So next important point, the elements in which the additional elements enter into n-2 F orbitals are called inner transition elements. So just like we had transitional elements, we have inner transition elements. So what are inner transition elements? So these are the elements in which the electrons or additional electron enters into n-2 F orbitals. So the valence electronic configuration of these elements can be represented as n-2 F0214 and n-1 D021 NS2. So it is n-2 F0214 and n-1 D021 and NS2. So 4F inner transition elements are also called as lanthanides. Why they are called lanthanides? Because I already told you that there is a lanthanum in transition element. So since they are coming after that lanthanum, so they are called as lanthanides because they come immediately after lanthanum. And 5F inner transition elements are called as actinides because they come immediately after actinium. So here you have two series. One is the 4F inner transition element series and the other is the 5F inner transition element series. So atomic and ionic sizes. So what happens to the atomic and ionic sizes of the F-block elements? So what is happening is interesting. So as the atomic number increases, each succeeding element contains one more electron in the 4F orbital and one proton in the nucleus. It's apparent, right? As the atomic number increases, the number of electrons increases, number of protons also increases. So the 4F electrons are ineffective in screening the outer electrons from the nucleus because imperfect shielding. So always remember, the F orbitals are poor screeners. So they are actually causing imperfect screening or imperfect shielding. As a result, there is a gradual increase in the nucleus attraction for the outer electron. So once we know that there is a poor shielding effect, what happens is that the effective nuclear charge increases because effective nuclear charge is inversely proportional to screening effect. Effective nuclear charge inversely proportional to screening effect or screening constant. So what is happening is that now because of the poor screening effect, suddenly the Z effective increases. As Z effective increases, what happens? The atomic radii also decreases, right? Because now the nucleus attracts the electron cloud with higher forces. So consequently what happens? There is a gradual decrease in size. This is called lanthanoid contraction. So what is lanthanoid contraction? Because of poor F screens, Z effective increases, and as Z effective increases, atomic radii decreases suddenly or decreases gradually. So this property is called lanthanoid contraction. So what are the consequences of lanthanoid contraction are important. Just like we knew what is lanthanoid contraction, the consequences also important. Because of lanthanoid contraction, there is a close resemblance between 5D and 4D transition series. The ionization energy of 5D transition series is higher than 3D and 4D. So difficulty in separation of lanthanides. Since most of the atoms have similar type of atomic radii, now it will be very difficult to actually separate it, right? Because all of them have the similar size. And also, now you know there is a 4D transition series and 5D transition series. Because of lanthanoid contraction, there is a close resemblance between this 4D and 5D transition series. Okay, so also it is also affecting your ionization energy, right? Because ionization energy depends on your effective nuclear charge also. As the effective nuclear charge increases, your ionization energy increases. So what is happening for the 5D transition series? Your ionization energy is higher than 3D and 4D. Why? Because of sudden increase in the effective nuclear charge. So the ionization energy of 5D transition series is higher than 3D and 4D transition series. Ionization enthalpies. So basically, one thing is that if you keep lanthanoid contraction aside, what is happening to the ionization enthalpies? So we know that as you go down the group, the atomic radii increases, right? So ionization enthalpy decreases, right? So obviously, compared to the top elements, the lanthanides and actinides have very low ionization enthalpies. That's the first important point. So the first ionization enthalpy, first thing is fairly low ionization enthalpies. So next important thing is that the first ionization enthalpy is around 600 kilojoule. The second is about 1200, comparable with the calcium. Due to low ionization enthalpies, lanthanides are high electropositive character. Compared to low ionization enthalpies to the period 1 and period 2 elements, they have higher electropositive character. Why? Because now I have very low ionization enthalpy, that means I can remove the electrons easily. If I can remove the electrons easily, they have higher electropositive character. Colored ions. Now this is another beauty of your F-block elements. So F-block elements can have or can form colored ions. So we know that why transition elements form colored ions, right? Because of d block transition or d block excitation or d orbital excitation. Similarly, the same thing happens in F block elements or F orbital transition. So many of the lanthanide ions are colored in both solid or in solution. The reason is FF transition, since they have partially filled F orbitals. So adsorption bands are narrow, probably because of the excitation within F level. So this is the reason why lanthanum 3+ and ruthenium 3+ do not show any color due to vacant and fully filled. The same concept of transition elements, why zinc was not showing any color. The zinc was not showing any color because it was having fully filled orbitals. The same thing now. Now La3+ and Lu3+, they do not show color because they have, one has vacant filled F orbitals and other has fully filled F orbitals. So thus we can see the same concept of transition elements of colors is applicable for the inner transition elements. So students, this is an introduction of your inner transition elements or F-block elements. The very important concept in this part is related to your lanthanoid contraction and the consequences of lanthanoid contraction. So if at all you are getting any question from this part, you will definitely get it from your lanthanoid contraction. So in our next part, I will be more discussing about the properties of your inner transition elements. Till then, just take care of yourself. Goodbye.